Welcome, everyone. Welcome to the session on using open data to fight air inequality, an introduction to the OpenAQ platform and its use cases. Thank you for being here today. And I'm Colleen Rosales. I'm the Strategic Partnerships Director at OpenAQ. And together with me today are the rest of OpenAQ, as well as our speakers who will share the use cases for OpenAQ. So some housekeeping and acknowledgements. We'd like to acknowledge and honor the people of the following nations on whose ancestral homelands and resources the land that OpenAQ staff reside is built. If you'd like to learn more about the nations on your where you reside, here's a link to do that. So some housekeeping rules, please don't forget to check in our Google Doc. And so you can find that on the Kiko chat where you were able to see the link for this room. And if ever you get lost, the short link to that is here. And then please don't forget to share your affiliation, your name, and where you are located on the chat and on the Google Doc. And then please feel free to ask questions and interact in the Zoom chat. I know in some rooms there was a Slido option, but I think we'd like to keep it to Zoom chat just so that it's more manageable for us tracking the questions. And then for after each presentation, we'll have a short time for questions, but we really encourage you to stay on until the end and join us in the breakout rooms where it will be more interactive and you'll have time for longer questions. And then when you're not actively speaking or presenting, please make sure to turn your microphone off. And then by participating in this session, you agree and adhere to the ease of community participation guidelines. And if there's any issue along the way, please don't hesitate to report in the third-party reporting as shown in here. And lastly, this session is being recorded and yeah. And so here's our schedule for this session. We'll start with an introduction to OpenAQ as an organization and OpenAQ, the OpenAQ website and platform by Chris Hagerbaumer, our executive director, and Russ Biggs, our director of technology. And we'll follow with a quick Q&A, and then we'll move on to a presentation by Dr. Carl Mallings from NASA. And then we'll again have a short Q&A, and then we'll have next will be a presentation from Dr. Collins Gameli Hodoli, who will also present another use case. And then we'll have a short stretch break and then a transition into the breakout rooms. And how these breakout rooms will go is that you can choose breakout rooms which you will join. And then you don't have to stick to the breakout room. You can jump from one to the other, but these are great opportunities to speak more about, or to converse and have more discussions about what was presented today. And then after that, 5 minutes before the top of the hour, we will all reconvene back into this main room, and then we'll end this session there. And so without further ado, well, I also would like to invite you to our social media and our presence on the web. And today is the last OpenAQ related session, but we'll always, be around in openaq.org and explore.openaq.org. And so without further ado, I would like to turn over the stage to Chris Hagerbaumer, our executive director. Take it away, Chris.
All right. Okay, can everybody see my screen?
Yes.
Okay. Let's see. That is weird. Because now I'm just seeing a big blank. Even though we tested this out. Sorry, folks.
You may want to go back.
Okay.
And then oops. Maybe go back on, okay, there we go. And then click the word slideshow. And yeah, there we go. There we go.
Okay. Well, of course, I lost my presenter notes, but who cares? Right. In any event, OpenAQ's purpose is to provide universal access to air quality data. We believe that air quality data is essential to empowering folks across the world to solve air inequality. That's the unequal access to clean air. And basically, we know that there's a certain number of governments across the world that are monitoring for air quality. A subset of those are actually opening that air quality up to the public. But even after all that happens, there are still problems that need to be solved with data. Typically, it's not fully accessible to the public, meaning sometimes that data is buried deep into government websites on some sort of PDF file. It's often in very disparate formats. Even at a national level or a subnational level, those formats might be quite different. That data can exist temporarily, and it's simply not designed to be globally or even nationally interoperable. So that's where OpenAQ enters into the picture. We want to solve those problems. So what we do is we aggregate that disparate data, any of that data that we can find across the globe, and we harmonize it so it comes out the other end much easier for folks to use. And then it's utilized for a number of diverse purposes. Here is a map, a current map of where we are getting our data. We've got 25 billion data points across the world from 48,000 locations in 150 countries. I will say this does not represent all the data out there because, again, folks are monitoring but not sharing their data. We can't get that. Sometimes the data that we had disappears because a URL changes or because a government decides they want to be more private with their data. So we're always out there trying to either recapture data or find new data. And we certainly could use your support if you know of data that's open but not on our platform. We primarily and initially collected data only from government air quality monitors, these reference grade monitors or research grade monitors. But the broader community expressed strong interest in us also connecting data from air sensors, also called low-cost sensors. So we started doing that in 2021 with Purple Air, Environmental Defense Fund, Carnegie Mellon University, and Habitat Map, and then have added more recently data from Clarity and SenState. And the great thing about this type of data is that in some places, it's the only data out there. If a country is not monitoring with reference grade monitors, this is helping to fill in key gaps, particularly in low and middle income countries and in environmental justice communities. We're collecting data primarily on the following pollutants on this slide. We do have, these are basically what would be called criteria pollutants by the US EPA, in addition, black carbon. But we do collect data on, let's see, PM1, PM4, nitric oxide, nitrogen oxides, and I might be missing one, but you will see some additional data, and actually Russ might share that a little bit, but these are really the ones that we have the most data on. So I want to go back and say that I mentioned before, many governments don't monitor for air quality at all. We initially did a report in 2022 looking at the landscape of who is monitoring and if they are monitoring, are they sharing that data? We have updated that report. We were pleased to release in just this past November a new report. And we found in that report that 61% of countries across the world, or governments, monitor for air quality. We found evidence of no monitoring in 39%. And then we found that just over half of the governments in the world are sharing air quality data. those who monitor, some are not. But what is particularly interesting is that you can share, but not really be sharing in a maximally useful way. So we looked at a number of different criteria for how truly transparent is that data. And we found that only about a quarter of the countries in the world are really providing maximally useful data to folks. I'll also say that of the countries that do not monitor, about 1 billion people are living in those countries and not getting any information on the air that they're breathing. We have a number of use cases for the OpenAQ database. I'll just touch on a couple of those. First, research. That's in fact a primary use. Those of you out there who are analysts, you are using our data to do research. This is just an example of one application looking at how did air quality change in the initial days of the or weeks or months of the COVID pandemic. This is a really fantastic resource from Bloomberg Green. You can go to this interactive data dash on their website, and you can look at what are the particulate matter levels in major cities across the globe. This is really, I think, a great example of journalism using evidence to provide information to people in a really, again, interactive way. So we love this. Another example is when a software developer creates an app that informs people about air quality. So the Smoky Air Pollution Bot is something you can find on Twitter or Facebook Messenger, and it's providing real-time air quality data and also communicating ways that you can safeguard your own personal health. Another great one is called Shoot, I Smoke. And the purpose that these software developers had was to really get into people's brain how serious an issue air pollution is by correlating it with cigarette smoke. Everybody knows that cigarettes are not good for your health. And this is a way to look and see how many cigarettes am I breathing today in this city, not wanting to actually breathe that. Again, both of these applications used the OpenAQ platform, and this one also uses WAQI, which I believe is based out of China. And then policy. What we really want to see is change on the ground. Urban Emissions uses data from the OpenAQ platform to provide information that is then used for long-term air quality management plans and to alert the public around public health issues so that they can take steps to reduce their exposure if at all possible. Another area that we're very interested in is just making sure that the community out there has the skills to use data, air quality data, to make change in their own communities. So in 2021, we launched something called the OpenAQ Community Ambassador Program. We just started out with these 5 folks from a variety of places. And this worked. What we did is provide training to help them use data in their day-to-day activities with their nonprofit or local government. And this was a successful program that we plan to begin again this year. Colleen will be leading it, and applications will be out for that program in late February. That's just the brief overview of what OpenAQ does, and I'll turn it over to Russ to then take us through some great new tools that we've developed. I'll get to stop sharing.
Great, thank you, Chris. All right, I'm going to share my screen here. Is that showing up?
Yep.
Wonderful, great. Well, thanks, Chris, for giving a good overview of what OpenAQ does, and I'm excited to share our new OpenAQ Explorer application. This is available at explorer.openaq.org. This is a brand new web application that we've been working on to help browse the large data set. So Chris gave some great statistics about the size of the data set, and I think it's great to see it on a map. You can kind of see the extent of the data set. But the size of our data set presents some issues, which is how do you find the data? How do you sort through all the data that we have available, and how do you start to look into what you're actually interested in terms of discovering more about air quality data. So this is the landing page of our new Explore app. You can see kind of the extent of the locations across the network. This new interface provides a couple of different ways to browse the data. First and foremost, you can filter by different pollutants. So we can, currently the map defaults to PM 2.5, which is what most people are generally interested in. We can switch over to all the locations that show PM 10 pollutants. As Chris mentioned, we have some core pollutants, but we also have some others that have that are in the system, different variations based on how sensors count data. So from the optical particle counters, we have that data. We also have the different subspecies of nitrogen dioxide from NOx and nitrogen monoxide. But within here, you can change between those different pollutants, and the map will update to show you where those locations that monitor those particular pollutants that you're interested in. As Chris also said, we we collect data from both reference grade monitors and air sensors, also known as low-cost sensors. So we've heard a lot from our community that with the addition of air sensors, this added a ton of data. There's about 27 to 30,000 of our data points are from air sensors. So here you can also filter out if you're just interested in the government reference grade monitor locations, you can filter those out. If you're just interested in air sensors, low cost sensors, you can filter those out. In this exercise of harmonizing lots of data across the world, data comes in at different frequencies. So sometimes monitors come online, come offline. So we've also added the option that you can exclude locations that haven't had recent updates. And this is defined as within the last 48 hours because it can kind of pollute the map for you. Also thinking of OpenAQ as a, as an aggregator of the data, we harmonize a bunch of different sources. So in our providers panel, you can choose the different sources, the data providers that you might be interested in. So in this case, if we're just interested in AirNow, which is the data platform that serves the US EPA, and that includes US monitoring sites for the EPA, but also Department of State reference grade monitors on different embassies around the world. We can select just the AirNow, and we can update our map, and now we can just see the extent of those. If I'm also interested in seeing AirNow and Purple Air, the kind of ubiquitous air sensor product out there, we can click that, and we'll update our map to show both those types of locations. So the primary goal of this is to provide you a way to start to see where the data is available on OpenAQ and help you explore better. We've also added some new functionality to help you just navigate the map a little easier. I'm based in Albuquerque, New Mexico, so I can just type in Albuquerque, New Mexico. It's going to find all the Albuquerques. There are other Albuquerques in the world, but we can go here. Our map will automatically zoom to my little slice of the world, and I can see all the monitoring locations near me. So now that I've kind of looked at my area of interest, I can pick a location, and we're going to get a little dashboard right here that shows some of the top level statistics, top level info about this location, when it was last updated, what types of pollutants it measures, and then the last 24 hours of measurements and the most recent reading of the two pollutants that it measures. So after selecting this Jefferson location, and we can see this is a reference grade monitor that's maintained by the US EPA, so it's coming from AirNow. We click on Show Details. It's going to bring us to our detail page. And here you can see it in more detail, info about this site. We can see recent readings over the last 24 hours. We will be extending this period so you can chart this stuff and see the general recent readings at different timescales and across different pollutants that are available. Really exciting new feature of the platform too is we've added some more info about the patterns of the data. So using these box plots, you can choose a different pollutant and you'll be able to see hour of day. So we can see some of this diurnal cycle of how time of day affects the pollutants at that particular location. Day of week, this can kind of affect some of those anthropogenic sources, like if this is nearby a high traffic zone, you might see more pollution during the weekdays versus during the weekend. And we can do the same thing for PM10 here and see a different trend. We also will be rolling out month of year, so you can start to get some of those seasonal signals available too. Finally, also on this page, there's an option to help you download the data in a CSV format. So in a quick and easy way, you can choose a date range, choose the pollutants that you're interested in, and then you'll have that data in a CSV format. Something to note is that this will have certain limits on the amount of data. So this isn't the best way to download lots and lots of data, but this will get you data from this location really quick and easy, and you can configure some basic pieces. So this piece as well is a good transition towards us wanting to help with education around how to use our other products, such as the OpenAQ API, which is the primary, kind of the best, the most powerful way to access data on the platform. So really briefly, we can go through there. As you change your download right here, it's going to update, and this is going to help develop the URL to access this data programmatically through the OpenAQ API. So we do have a documentation site, which is docs.openaq.org, which has got this really great interactive documentation. So if you're programmatic, work in programming languages or computer inclined, this is a great way to have a really powerful access to the full OpenAQ data set. And this allows for large data, much more flexible, larger downloads. And this is how some of the application examples that Chris shared can have interacted with our data set and are able to build atop the OpenAQ platform. So within here, we can learn, there's lots of different ways to learn through how to get the measurements, how to get locations, and you can build interactively a URL to access this. Also has these great examples of how to use the programming language or platform of your choice across, I think it's got 20 different languages. So if you know whatever programming language it's probably got some options for you. Also, in the interest of trying to educate more about the platform, our documentation site also has a recipe section. These are currently written in Python, but we will be looking to add more languages. These are some common recipes that people are kind of interested in. So how can I list all the OpenAQ locations by country? How can I find a single location? How can I find locations, but also filter to PM 2.5? So I do recommend checking out the documentation site, docs.openaq.org. It's a great resource to start to get involved if you want to start to use the OpenAQ API. Like I said, these are just two tools that allow you to access the database. I'm going to go ahead and stop there in the interest of time so we can kind of catch up. If anybody has any questions, I'd be happy to answer.
Thank you, Russ. Thank you, Chris. Yeah, do we have any questions from the audience? And we'll also have, time at the end to further explore. Alrighty. So I guess, well, I have questions, but I'll reserve them for the breakout rooms. So in the interest of time, we'll move on actually, we have a question from Phil Yang. Maybe Chris, if you can answer in shortly. So do you have collaborations with the local community? I guess, do we have collaborations?
So that is something that we are working towards, sort of meeting with some of the local groups. And actually Collins can kind of give an example of a collaboration in his presentation. But we're an incredibly small staff. So we don't actually have the ability to provide a lot of technical support to local communities, but that's something that we want to build. And what we're really trying to do is build tools that are more easily usable by people, that are more intuitive to folks to use. So it's something that we're working towards, but it's not something that we've really had a lot of capacity to do.
Great, thank you, Chris. So we'll move on to our next presenter, Dr. Carl Mallings, who is an assistant research scientist at Morgan State University and is now working at NASA. Take it away, Dr. Carl.
So thank you very much. So as was mentioned, I work at the NASA Global Modeling and Assimilation Office, or GMAO. And in this presentation, I'll hope to give you a very brief overview as to why open data in general and OpenAQ data specifically are important to the air quality work we do there. A little bit of a background for anyone who's not familiar with air pollution who happens to be in the meeting. It's a major global issue. For example, this recent global burden of disease study ranked it as the leading environmental risk factor for premature mortality around the world, and attributed about 7 million premature deaths to poor air quality or air pollution in 2019. So it's a major global public health issue. And NASA, being an agency that has a lot of information about the state of and composition of the atmosphere, which is relevant for air quality, does have a role to play in providing the data to address this issue. So in terms of the sources of data we use to understand air quality, on this slide, I've grouped them into two broad categories. On the top, you have global or regional data sources, which cover things like atmospheric chemistry simulation models and remote sensing observations from satellite-based instruments. This is really where NASA is most involved. And these give us sort of a top-down overview of air quality over the whole world or larger regions of the world. And on the other side of the spectrum, you have from the more local data sources, which was discussed in the previous talk, including things like regulatory monitors and low-cost sensors or air sensors, where those are available. And those really give the local level information on what the air quality is, where people are actually living and working. And in this presentation, I'm going to try to make the case in general that it's very important that all of these data sources be open and that they work well with each other. And that's a place where OpenAQ, as well as others, play a big role in making that possible. Starting with the global level, in terms of atmospheric chemistry models, there are many agencies around the world, including NASA, that develop these Earth system models, which aim to simulate various aspects of the Earth system, including the air and atmospheric chemistry as it relates to air quality. So specifically at the NASA GMAO, where I am, we have what's called the Goddard Earth Observing System Composition Forecast model, or the GOCF model system. And that's run every day, and it produces an analysis and then a 5-day forecast of the atmospheric composition, including parameters which are relevant for air quality. As with many agencies, we have a mandate to make those data publicly available, so we do that. But in addition to just sort of making the raw outputs available through our website, we've tried to increase accessibility of the data, as was also mentioned in the previous talk, allowing different users and different people with different levels of experience to work with the data. So some examples of that: on the left, I have the Fluid online visualization tool for our GOCF product. You can go to this website, it'll bring up a map. You can zoom, pan, and click on individual points to bring up the history and the forecast data for the air quality at those specific grid cells of the model. And then we've also, through a NASA-Google partnership, started uploading the GOCF outputs into the Google Earth Engine online data analysis and visualization platform. So that's just another example of how we're making these, not only making the data freely available in the sense that it exists online and you can access it, but allowing people to interact with the data in different ways to open it up to different communities. Similarly, for satellite data, NASA and other agencies which operate these satellites, which provide information relevant for air quality, typically make them publicly available. NASA does that in a couple of different ways. On the left, you have websites like Worldview and Earth Data, which allow you to go online and bring up visualizations of data from these satellites and download the data for your own local analysis. And then we also have web-based tools like Giovanni on the right, which is an online simple data analysis platform. You can do simple tasks like temporal and spatial averaging of various data sets, and then just visualize the results right on the platform or download them yourself to do your own analysis. So again, just different ways of making data accessible and available to different groups with different needs or different levels of expertise. As was mentioned before, for the local data, they generally come in two broad categories: the more regulatory-based monitoring, typically government-operated, and the low-cost sensors, typically individual or community group or sometimes university group operated. And there are different levels of accessibility and availability for these data depending on who's collecting them, as was discussed in the last talk. Just looking at this in a little bit of a different way, this is an example of an analysis I did recently using the OpenAQ data and API that was mentioned in the last presentation. And this is trying to look at the number of, in this case, PM2.5 monitors per million people aggregated on a country and then on a regional basis, and the horizontal axis plotted against the estimated annual average PM2.5. This comes from a satellite-derived data set on the vertical axis. Now, as was mentioned, this is not necessarily every monitoring site. Some of them are not made publicly available, and so they're not on OpenAQ, but I think it gives a good general impression. And there's a couple of broad conclusions you can draw from this. First, you can see the regional disparities in terms of the density of air quality monitors, with some regions which have typically the highest levels of PM2.5 having some of the lowest per capita monitoring availability of PM2.5. And even regions that are fairly well monitored, they rarely more than about 100 monitors per million people, which, considering the variability in air quality, especially in urban areas, is really not enough to fully capture the air quality situation. And then finally, you can see the impact that low-cost sensors are having in this space, increasing the relative density of air quality data availability in some regions by up to an order of magnitude. So very important source of information. So all of this is to say that because of the differing levels of data availability for surface-based measurements and the relative scarcity of these data in many regions of the world, it's really important that these data be made openly available so that we have access to them and can use them. So how do we go about using them? There's a couple of general use cases that we take at the GMAO. One, this example is from my colleague Viral Shah at the GMAO, and he's using open data from the AirNow API, which was mentioned previously, for surface level ozone monitor. That's on the left plot, and he's comparing that with our analogous quantities from our GeoCF model forecast, the 1 day ahead forecast in the center plot, and showing the differences in the right plot. Now, in this case, there was a significant bias. The model was actually overestimating these concentrations by quite a bit. And that was a known issue in the model, but to really look at the spatial extent and the degree of this issue, we wouldn't have been able to do that to this, certainly not to this extent, without high level access to vast quantities of surface measurement data, which was provided through the AirNow API in this case. And if we want to do this on a more global scale, we would need aggregator platforms like OpenAQ to make that possible. So going beyond simple comparisons, this is an example of a project that my colleague Christoph Keller at the GMAO, as well as others at NYU and the World Resources Institute, are working on, called the CityAQ project. And one of the goals of this project is to develop or to implement an algorithm developed by Christoph Keller, which combines the GeoCF model output data that I mentioned with local monitoring data and creates, based on that, a bias correction for the GeoCF forecasts to bring them more into line with the ground truth and to reduce the biases that I showed in the previous slide. So this is just a screenshot illustrating a tool that's currently being developed for this by Nusseir Lazrak at NYU. And it's basically showing how, in this particular example, he's taking data from certain sites which are sharing their data through OpenAQ and implementing the algorithm for those sites with the vision that eventually this tool will be available and applicable and capable of being applied to all the sites that share their data openly, especially through the OpenAQ platform, to just basically improve the location-specific accuracy of the forecast we can provide. And finally, I want to talk about a project that I'm getting involved, or the project starting out with, and I'm involved with it. It's supported by the NASA Applied Sciences Health and Air Quality Program. And this is, again, aiming to develop a web-based application that will combine the global data sources like the GeoCF model and various satellites with local data sources, both regulatory monitors and low-cost sensors, and combine these using a data fusion tool implemented in Google Earth Engine, which will allow for location-specific estimates, city-specific estimates and forecasts of air quality, covering, as opposed to the previous example, the CityAQ example, which was a point-specific forecast. These would be more area forecasts, as you can see some examples of at the bottom. And this is just a screenshot of a prototype version that we're currently working on, but you can see the background in purple is the surface level NO2 estimate, which is a combination of the model and some satellite data to improve the spatial resolution. And then we're integrating that together with the local data sources in the green and the blue circles representing the regulatory and low-cost monitor data. And this is just an example of what that looks like, showing how as you add more data sources together, you get kind of closer and closer to the expected value that we're trying to get. Again, this is still work in progress, but you can really see the power of having access not only to all these different open data sets, but also to an open analysis platform like Google Earth Engine, which allows you to bring all these data from different sources together and do analysis in an open way. Just to summarize briefly what I've said, in terms of sources of data, both the global sources like model and satellite data and the local sources like the low-cost sensors of the regulatory monitors, it's very important that all of these be open from the get-go. And not only that the data then be open in the sense that they are available, but they need to be accessible, which means having web-based tools to look at the data, API access. And this is where aggregators like OpenAQ really come into play by bringing together data from different sources all together in one place, systematizing the formats, getting the metadata in the same format, which allows end users to do the kind of filtering that was shown in the previous presentation. So that's a really powerful tool for researchers and for anyone working in air quality. I showed some examples of some use cases we have, which range from simple, verification of one data set against another to integration of multiple data sets to gain some more insights into the air quality situation. And for the latter, that's really important, not only to have access to the open data themselves, but to have an open platform like the Google Earth Engine example I showed, which allows you to sort of implement the algorithms and really do that analysis in an open way as well. So with that, I'll stop and maybe I have time for a quick question.
Thank you so much, Carl, and thank you for driving home the point of the importance of open data for air quality analyses and air quality applications. So we do have a question from Gabe. What are the main sources of bias in GeoCF and how do they affect the overall performance of the model? And then are there any particular regions or variables that are more affected by bias than others?
Yes, and both because of time and my lack of expertise, I can't go into full details about this, but I think in general, I would say one thing that for all air quality models, including the GeoCF, they really rely on the emission inventories, which tell the models what's being emitted into the atmosphere, where and when and how much is being emitted. And those are very regionally dependent in the sense that in different regions, these inventories are kept up to date in different ways, they're managed in different ways. So there could be very, very big regional differences in how accurate and how complete these inventories are, which leads then to the model, inheriting those regional disparities, which affect its performance in different regions. So that's very quick one aspect of your question, but yeah, you can kind of look up publications on this if you want more details, or we can talk a little bit more later.
Thanks so much, Carl. And we'll move on to our next presenter, Dr. Collins Gamelli-Hodoli, who is a lecturer of smart technologies at the University of Environment and Sustainable Development. He's also the founder and director of operations at Clean Air One Atmosphere. Take it away, Collins. Collins. There we go.
So great. Can everybody hear me, please?
Yep, we can hear you.
Awesome.
Okay.
So just going to do a brief on the usefulness of citizen science in combating air pollution and in low and middle income countries. I will do a case study from Ghana. So before then, I want us to keep this in mind. The converse should hold that no person or body should presume that their views are right to the exclusion of others. But those of us from these parts of the world where there is destitute, we must find new discoveries and application of theories of science to address our destitution. So just a bit of the presentation will be who we are, the need for what we do, and using do-it-yourself, and Internet of Things with air sensors, bridging the air pollution public knowledge gap, and then some results from the use of air sensors. So we're just a small group, talented and dedicated professionals with backgrounds in computer science, business administration, and environmental science. So what is the need for what we do? Air quality monitoring, just even listening to the presenters who have earlier talked about these air pollution, the key point is that air quality monitoring is undertaken by regulatory agencies. So that's the global norm. And this limits our understanding and participation of air pollution related impact. Then the key part again is that the available air quality data in the region, that is in Africa, in Ghana, it's poorly communicated. This was highlighted in Chris's presentation as well. Now, it hinders our understanding of air pollution and its adverse effects on human health, environment, ecosystems, including agriculture. So what happened is that we have very poor developed air pollution mitigation policies or strategies because the public do not understand the need for implementing mitigation strategies or air pollution management and control protocols. So what we have been doing with air sensors, the instruments that we use, basically clarity notes, air note monitors, purple air sensors. We actually started with purple air sensors. And then because we use low-cost sensors or air sensors, we have to follow some protocols, which is quality assurance and control. So we co-locate these sensors with regulatory monitors to be able to understand how they sample the same air with the regulatory ones. So do some comparison and see whether it will fit for purpose. So then in terms of data analytical methodology, we use the widely accepted open air packages and the open air manual for air pollution data analysis. Oops. And so we have been doing some works in Ghana. We started in Ghana, extended to Togo, Benin, and the Gambia. So we deploy air sensors for monitoring PM2.5 in selected communities in collaboration with local and international research institutions, as well as local government agencies. So in Ghana, we work with the Ghana EPA. In the Gambia, for instance, we work with the Ministry of Health. And so what we have done is to leverage open source data for expanding communities' understanding of air pollution and its impact on health. So this is a use case where you look at the meaningful communication of air quality data. The point is that the regulatory data from Ghana, for instance, is not well communicated. So we have developed a mobile application, which is currently still an Android version. And so we pull the data from the Purple Air map, which is actually picking the AQI or the air quality index. So the first thing you see in the round circle here, where the cursor is hovering, is the air quality index. So we understand that the higher this number, the more polluted the air is. And then the one at the bottom, which is a triangle, is just telling you or telling us the location where we are picking that data from. So this is from a location in Ghana, one of the secondary schools in the Eastern region. The one at the bottom is providing health tips. And the other part is we define what the AQI is. And then there's also a part which tells you how as an individual, we can reduce air pollution. The key part of this is to actually look at the fact that how do we bridge the gap between communication and also influencing behavioral changes. And the figure B is just telling us where exactly on Google Map this sensor is located. And the C it's just a time series plot of the AQI. And then the D, because health surveillance data is not pretty much a good thing when you come to Ghana, we're trying to see how we can collect some data of a sort to support air pollution health effect studies. So just a bit of a thing that what can we do with open source air quality data? These are low cost sensor data, but then how do we leverage that to address some of the challenges that we have when it comes to air pollution management and control? So these are, this is from air note monitors we had co-located at the University of Ghana, Legon. And so we compare the data from that to regulatory data, Teledyne T640 PM mass monitor. So this is for PM 2.5. And then we can see that all the air node monitors actually underreported for PM 2.5. So the red and the black lines, that is what we see. But then there is a high consistency between these two nodes. However, there is underreporting. So we need to correct for that. So again, all PM 2.5 measurements from the air sensors correspond or confirm to atmospheric measurement principles. I have not shown the temperature and relative humidity, but comparing the two, there is that inverse relationship between that. Then also, we could see that the out of the box values for all air node monitors ranges from a little below 15 and then to 81 micrograms per cubic meter. So we have tried to look at the correction for this. And what we did was to use a multiple linear regression model for that, and then a split ratio of 0.8 and 0.2 to train and test the data. As you can see, the figure A, this is the raw air note monitor data against the regulatory one, Teledyne T640. And we can see that there is a very poor relationship when you compare that. And then the R square for that is 6.9. But after applying the correction, we can see that there is a very good correlation. And then our R square, we used the Pearson's correlation analysis that resulted in R square of 0.84, which is a great thing looking at the quality of the data. And so we see an improvement from 0.69 to 0.84, and then a mean absolute error also from 11.75 to 4.20. Looking at that, we wanted to see again, how does the corrected data correspond to the regulatory data? And we can see a clear improvement in that. And so we have seen that hourly average PM 2.5 values ranged from 25 to 95 micrograms per cubic meter. If you look at it 24 hours, it's 29 to 54, which is more than the WHO recommendation of 15 micrograms per cubic meter for PM 2.5. And so we have also realized that there is also underreporting, again, even though there is a correction factor which has been applied. So what does this mean? This means that we would have to look at ways that we can improve these. So maybe other methods for correction. But a key part is that if there is an open source data, citizens can leverage this to be able to do these types of analysis and then, improve the data and engage policymakers locally to be able to put in some mitigation strategies. Now we're trying to see, looking at air sensors, what role can they play in our part of the world? And so we have looked at the corrected data, the raw data, to try and triangulate the sources of PM 2.5. The figure C is the regulatory data, and the one in the middle, the B, is the raw data from the air notes monitor, and the A is the corrected. As you can see, there's a clear pattern of a common source, which is actually saying that even as you look at the corrected, the raw and the regulatory, they all point into a similar source, which is saying that PM pollution is local and basically from the southwest winds. And then if you look at it locally at very low wind speeds, you're seeing pollution at very high levels, and even from the north and northeast as well. So even though there are disparities or there are variations in the concentrations, you can see that the sources are the same. So the point we're trying to make it is that how do air sensors and open source air quality data fit into addressing air pollution in our parts of the world? So it'll be useful that we use them to actually triangulate sources, and also great that we improve the data to meet a level that can be accepted by regulatory authorities. So the key takeaways: air sensors are useful for advancing community engagement. What we have been doing is that moving to secondary schools and even universities to deploy air sensors, collect the data and engage students, train them on how to actually understand that. And these are targeted at influencing behavioral changes. And to be able to understand local air quality, we need to have site-specific monitoring. So if there is an open source data which is actually picked from my location, I can use that to understand what is going on in terms of air quality. To be able to understand sources, we need auxiliary data, particularly wind component data, to do that. And then we have also realized and established that air sensors are useful for democratizing air quality monitoring in environments with limited air quality data, which is our region. So meteorology as well plays a role. And then the fact that there's a consistency between the two air nodes that we have used means that we can use them in similar environments, and also the correction factor that we have developed will be able to be applied in that environment. Thank you very much.
Thank you so much, Collins. And that's a great testament to, how open data and as well as how the landscape has changed with the advancements in air sensors. And so we thank you for this presentation. I'd like to open the floor to questions from the audience. I have one question. I noticed that the correction that you did with respect to the reference monitors, they were February, is that right? The time range was February until March. Okay, so do you anticipate that in different months, the corrections would still be under-corrected, or would the air notes still be under reporting, say in a different month, if you were to calibrate on a different month, or, how do you expect the behavior to change?
Yeah, I think there's a possibility of having a change because for you to fully understand this, there should be a long-term data, but because this was just for research purposes, we wanted to just test that. And once there is a variation in seasons, there will be different reactions, and there will be, for instance, if it is Harmattan, there will be changes as well. But a key part is, will these corrections fit for purpose? That is a question we should be asking. And then if the data is improved to a certain degree, can we use that to make some informed decisions? Thanks for your ask.
Totally agree. So we have another question from Gabe. What is the biggest factor in differences of air quality monitoring data values between sources? So Gabe, did you mean in general, or between the monitors that Collins has used? So I know you mentioned.
I guess I was curious if it was environmental, or if he thinks it's just because of the difference in hardware.
Right. So just to point out, I'm not so sure the type of instrument will affect the source of air pollution. The key thing is whether, or the consideration should rather be given to the background activities and the level of correction that is applied to the data, as well as aerosol constituents. We are looking at PM 2.5. So what could really be the contribution if you consider that in relation to background activities? I'm not so sure if that answers you, but the instrumentation types you actually not affect the source.
Yeah, no, I didn't mean the source of pollution. I just meant the data source.
That's an important distinction. But so thank you, Collins, and thank you again, Carl, and thank you, Chris, and thank you, Russ, for all the presentations. Now I think it's time that we will move on to our breakout rooms where we can discuss more of our questions and our curiosities about OpenAQ and the use cases that have been presented today. So a little bit of briefing about our breakout rooms. We will have 3 breakout rooms. You're free to join whichever breakout rooms that fit your curiosity. So except for Carl and Collins, I have and the OpenAQ staff, I've assigned you to rooms. So the first breakout room would be for technical platform and API questions. And so Russ and Gabe will be there. Next would be breakout 2 would be for partnership questions or collaboration questions, as well as questions for our speakers. And so Carl and Collins and Chris and Colleen, which is, I realized we're all letter C. I didn't put that on purpose, but we're all going to be in that breakout room. And the last would be an open networking breakout room. And you're free to move to, different breakout rooms. Not holding you hostage in the breakout rooms, but please feel free to join whichever breakout room suits your questions or your curiosities. And again, you're welcome to put your notes on our shared Google Doc as well as on the Jamboards that are specific for each breakout room. And before we move on, so I think we're running a little bit behind, but that's okay. We do have, a bit of a time for the breakout room. So why don't we take a 5-minute stretch break? Please don't go anywhere. I mean, don't leave if you leave, make sure to come back and interact in the breakout room. But let's take a 5-minute break. So right now it's 2:29 for me. Let's go back. Well, let's make it 6 minutes. So that's an even number. So let's go back at 2:35. And so we can, Allison and Jake, maybe if we can already open the breakout rooms, and then we can take the break in the breakout rooms if that's okay. And then, and then, start the conversation at 2:35. And then after the breakout rooms, we'll come back to the main room just to say kind of goodbye to everyone and have some closing remarks. So I see the breakout rooms have now popped up. It should have also popped up for everyone, and you're free to choose the breakout rooms and chill out there for a little bit. And then, happy conversation to all. See you in a bit. All right, I think we have everyone back in the main room. I hope so. I think we had 2 breakout rooms, and I'm glad that it seems like everyone had good conversations. And I hope this is not where the conversations end. As I mentioned in our breakout room, we're part of the air quality cluster of ESIP, and so we all invite you to catch us there as well as outside of that. So again, I listed here the channels where you can reach OpenAQ. We also invite you to explore our Explorer tool. And if you have, leads or ideas on where there's more air quality that we can put an OpenAQ, please do let us know. With that, I'd like to thank everyone here today, and I'll see you around. Have a good day, everyone.
Thank you so much. Thank you, everybody, and see you around.
Thanks, everybody.
Thanks, all. Good session. Bye-bye.
Thank you. Bye.
Bye-bye.